In this section, section 5.2, we're looking at verifying trigonometric identities. So you should have already learned about what identities are in the last section, remembering that identities are just expressions that show equivalence, right? Expressions that show equivalence. Like, for instance, we saw that 1 over the sine of an angle is the same as the cosecant of an angle. And those are the most basic, the simplest identities. So now we're going to be looking at expressions that are much more complicated than this. And the goal is to do something called verifying the identity. Verify the identity. That means that your job is to prove that both sides of the equations are equal to each other. Right? So for instance, can I show that x squared minus y squared equals x minus y times x plus y? That's a common algebraic expression or identity. We want to do the same thing with trigonometry. So every time we do one of these verifications, the goal is to transform one expression until it is exactly the same as the other expression on the other side. So I might take the expression on the right-hand side and try to make it look identical to the expression on the left-hand side. So each time we go through and we make these changes, we want to be able to justify those changes using some sort of identity that we've learned. Every identity is going to be unique, and so as we look at these identities, we want to have a set of strategies that we can use to figure out which direction we should go. So here are the most common strategies, these 6 strategies. One is we should always work on simplifying the more complicated side. It's always easier to take something complex and break it down and make it more simple, as opposed to taking something simple and figuring out how to make it more complicated. The other thing that we might look at is if there are 2 fractions in the expression, can we combine those fractions? We might work to multiply both sides of an equation by the conjugate. So remember, the conjugate of a plus bi is a minus bi. So meaning all we're doing is changing the sign between. If it has really large exponents like squares or cubes, we might be looking to factor. And we could factor in all kinds of different ways, the way we learned from algebra, or even just taking out the greatest common factor. Sometimes we take all of the terms and we rewrite all the terms as either a sine x or a cosine x. And lastly, if you have a fraction, you could work on splitting that fraction. So for instance, if I had 1 plus cosine x all over sine x, what I mean by split the fraction is distribute the division. So this is going to become 1 over sine x plus cosine x over sine x. So sometimes that's a good way to simplify an expression. So let's take a look at a couple of these. So here's our first trigonometric identity. Let's take a look at it. So you can see that this is the more complicated side. So that's the side I'm going to work on simplifying. And I'm actually not going to touch the other side. I'm going to try to just focus on the left-hand side. So the first thing that I'm going to do is I'm going to notice that in the numerator right here, this guy, cosecant x squared minus 1, is actually an identity. It's a Pythagorean identity. So I'm going to use a Pythagorean identity to replace this expression cosecant x squared minus 1 with cotangent squared x. And I'm going to leave the denominator alone. Okay. And in the next part, I'm going to simplify cotangent squared x over cosecant x by rewriting cosecant as 1 over sine squared and rewriting cotangent as cosine squared over sine squared. So this guy becomes cosine squared x over sine squared x, and this guy becomes 1 over sine squared x. Okay, so this becomes cosine squared x over sine squared x times sine squared x. And now you can see from here we're just going to have some algebraic simplifying. The sine squareds cancel out, and we're left with cosine squared x, which is exactly what we had on the right-hand side. And the last step of my proof should always show that the two sides are equal to each other. So I have cosine squared x on the left-hand side and cosine squared x on the right-hand side. So there is usually more than one way to verify an identity. So we just looked at this exact same problem, but you can see here that it's been solved very differently. So this one was written as the difference of two fractions. In other words, it was split the fraction or apply the distributive property. And then each one of these was simplified. And then lastly, 1 minus sine squared x is a Pythagorean identity, which can be turned into cosine squared x. So how do you know which direction to go? Well, it doesn't really matter which direction you go. You can go in any direction that makes sense to you, and you might go in a different direction than somebody else. Sometimes the direction you go seems really hard. You might stop and go in a different direction. All right, let's look at another one. This time we're going to see what happens if you try to combine fractions. So what do I mean by combined fractions? Can we add these two fractions together? Well, sure we can. We just need to make sure we have a common denominator. So I'm going to use, for my common denominator, the product of these two denominators. So this is going to become cosecant x minus cotangent x all over cosecant x plus cotangent x times cosecant x plus minus cotangent x. So this is what I've multiplied the top and bottom by. Okay, and then for my other fraction, I'm going to multiply by cosecant x plus cotangent x. And the denominator is going to be cosecant x minus cotangent x times cosecant x plus cotangent x. And over here, this is what I've multiplied by. Okay, this looks crazy, but the numerator becomes cosecant x minus cotangent x plus cosecant x plus cotangent x. And the denominator is going to be multiplied these two binomials out. And because it's like a plus b times a minus b, it actually simplifies into cosecant squared x minus cotangent squared x. Now again, this isn't really even that crazy looking because these guys cancel each other out. Those are gone. So I'm left with 2 cosecant x. And then this guy right here is a Pythagorean identity. And he simplifies into 1. So what do I have? On this side I had 2 cosecant x. On this side I now have 2 cosecant x. That's exactly what I was hoping to have. And I'm done. All right, so here's an example of when we might multiply by the conjugate. So you can see on this side I have a 1 minus cosine A. So I'm going to take that and I'm going to multiply the top and bottom by the conjugate of 1 minus cosine A, which is 1 plus cosine A. And just like in the last problem, when you multiply A plus B times A minus B, you just get 1 squared minus cosine alpha squared. Okay, so I'm going to leave the top alone, but I'm going to convert this guy into sine squared x because that's a Pythagorean identity. And I'm going to write it as sine A times sine A so that I can cancel these guys. Okay, so now I'm left with 1 over sine A plus 1 over cosine A. And I'm going to do that trick again where I split this into two fractions. This is going to be 1 over sine A plus cosine A over sine A. And I'm almost finished. I'm going to bring mine around over here. 1 over sine A is cosecant A. And cosine squared A over sine squared A is cotangent A. And that's exactly what I was hoping to get. Cosecant alpha plus cotangent alpha, right? This is what I was hoping to get. All right, success. All right, so again, here are 2 different ways to solve this problem, right? Here's an example of where we multiplied by the conjugate. This is the method I just showed you, right? And then we simplified, and then we used a Pythagorean identity, right? And then we split it into 2 pieces. But you can see over here, there's an entirely different strategy. This time the strategy is to take the right-hand side, cosecant alpha, cotangent alpha, and to rewrite these in terms of sine and cosine. This is one of the strategies I mentioned at the beginning. So rewrite everything in terms of sines and cosines. These fractions add together because they have a common denominator. Then we can multiply the numerator by the conjugate. And once we do that, then we see that the left-hand side is the same as the right-hand side, and we're done. Okay, last one for verifying. So you can see that this one has a lot of tall exponents. So one of the things that I'm going to do is notice that there are some common terms here and here, and I'm going to factor those out. So I'm going to factor out cotangent theta, secant theta. That cancels here, and that leaves me with cosecant squared theta. I'm going to take cotangent secant out of this guy. That cancels one of these, leaving me with 2, and cancels this one, leaving me with cotangent squared theta. Okay, so in my next step, I'm going to recognize that this guy right here is a Pythagorean identity, which is equal to 1. So I get 1 times cotangent theta secant theta. And I'm going to use that strategy where I'm going to rewrite everything in terms of sine and cosine. This is cosine theta over sine theta. This is 1 over cosine theta. These guys cancel, and I'm left with 1 over sine theta. And in my last step, I'm going to write 1 over sine theta as cosecant theta, which is exactly what I was hoping to get, because that's what I had on the right-hand side. And I'm done. So the last thing we're going to look at in this section is how can you tell if 2 sides are equal to each other? How can you tell if it's an identity? And the answer is, if it's an identity, these are all the different strategies you can use, right? And we just looked at a bunch of these strategies as we applied these problems. If you're not sure if it's an identity, you can check to see if it's an identity by graphing the functions and see if they have the same graph. So for instance, how can I tell that this is an identity? Well, what I did was I can take the graph y equals cosine x plus 1 over tangent squared x, and I can take the graph y equals cosine x over secant x minus 1. And I can graph these 2 things, and I can look and see if their graphs are identical. Since the graphs are identical, it is in fact an identity, and then I would go about verifying the identity.